Hello pre-calc honor students, here we are with the area of a triangle 9.2. We're going to do for a specific area formula, that is the area of a triangle given the lengths of the two sides and the measure of the included angle. You studied this in geometry a lot with the idea of side angle side, where you're given two sides and the angle between. And that determines a unique triangle. Okay, now we're going to find the area of this using what we just learned from SOHCAHTOA. I'm going to start by dropping a perpendicular down this way. And so this is angle C, and this is side A. You note the convention that we use the lowercase letter for the side and the uppercase letter for the angle. And so this is side C over here. So we can see now that we've got some height that we need for our traditional area formula. And we'd like to use K for the area of a triangle. 1/2 base times height. 1/2 base times height. But in this case, we have the base B and we have the height H, but what we don't have is H in terms of A, B, and C. So I'm going to focus on the little right triangle here. Focus on the right triangle that has this C here, and this is H, and this is A. And let's use SOHCAHTOA to relate these. H is opposite angle C, and A is the hypotenuse. Ha ha, ho ho, oh, SOHCAHTOA. So we're going to say the sine of angle C is the opposite side H over A. So A times the sine of C equals H. So now we can finish our formula here. We had K equals 1/2 BH, and now we can substitute in A times the sine of C for H. So we get K equals 1/2 B times A sine C, or more simply written as 1/2 AB sine of angle C. And we can do that with the other sides as well. And so the area formula for the triangle, if you have two sides, you can say 1/2 AB sine of angle C, or you can say 1/2 BC sine of angle A, and that'll equal 1/2 AC sine of angle B. In English, the area of a triangle is half the product of any two sides times the sine of the included angle. Now let's try this in our first example. Two sides of a triangle of length 7 and 4. The angle between the sides measures 73 degrees. Find the area of the triangle. So we can say the area equals 1/2 7 times 4 times the sine of 73 degrees. So K equals 14 sine 73, and let's put that in the calculator. And I get 13.388. That checks with 13.4 square centimeters. Okay. All right. Now, let's take example 2. The area of a triangle, PQR, is 15. If P equals 5 and Q equals 10, find all the possible measures of angle R. Well, let's take a look at this first on GeoGebra. I think I have that right here, example 2. Here's P, Q, and R, and we want to find P equal to 15. And what I've done here is I created something where Q will always stay 5 away from R, so I have side P as 5, and side Q is 10. Notice how P always stays 10 away from R. That's because I put them both on a big circle. That's the circles you see right here. That circle and that circle. So it's a nice trick to make sure we have those sides. Now we can look at all the possible options as we change side P and side Q. So we're trying to get an area of 15. Right now the area of the polygon is 20. So if I go like this and make it a lot smaller, the angle a lot smaller, see we're getting closer and closer to 15. So here's one answer over here, about 36 degrees. And then we also see we get another answer over here. We can also get 15 with an obtuse angle there, about 143 degrees. Let's see how this works out with the trigonometry. We're given the area of the triangle, and we know area equals 1/2 any two sides times the sine of the angle between, which is r. So the area is 15, and we have P is 5 and Q is 10 times the sine of angle r. So we're getting 15 equals 25 sine r, or the sine of r equals 15/25, which reduces down to 3/5, or 0.6. So remember, that creates a trig equation of sine of r equals 0.6. And from, remember, our unit circle analysis, we'll get a y coordinate of 0.6 in two spots, in both the first and the second quadrant. We get one answer just by taking the inverse sine of 0.6, and we dig that up on our calculator, giving us 36.9 degrees. And to get the other answer in the second quadrant, we'll have to subtract, for a second answer, for our 180 minus 36.9 degrees. And that's where we get as another possibility 143.1 degrees. So we get two possible values for this triangle that will both make an area of 15. And that's something you have to be careful of. When you use sine to solve for an unknown angle in these general triangle problems, whether it's area or, as we're going to see tomorrow with law of sines, you might end up with a couple possible answers. Now, for our last example, I want to review again the idea of segment. We looked at a few of these in the first semester after we learned our area of a sector. But basically, the segment of a circle is the region bounded by the arc and the chord. And you can find the area of the segment by subtracting a triangle from the area of the sector. So to find the area of this segment in here, here's the segment. Now, I know we've also talked about line segments, but the segment of a circle is this area between the chord and the arc. You can do that by taking the area of the whole sector, and we had formulas for that last chapter, minus the area of the triangle, which has 2 radii for its sides, and this chord for the other third side, and the central angle theta there. Now let's review our formulas for these two. Remember, if you got the radiuses and the angle theta, you can do the area of the sector by 1/2 r squared theta, or 1/2 rs. Usually we're going to be knowing theta, so we're going to stick with this 1/2 r squared theta, as long as theta is in radians. And for the triangle now, we have 1/2 r times r squared times the sine of angle theta. So very similar formulas, but notice we take the sine of the angle when we're doing the area of the triangle. We don't do that when we do the area of the sector. So that comes up in this last example. The diagram shows an end view of a cylindrical oil tank with a radius of 1 meter. Through a hole in the top, a vertical rod is put down in here. And when the rod is moved, the oil level in the tank can be read from the oil mark on the rod. Where in the rod should marks be put to show the tank is 3/4 full, 1/2 full, and 1/4 full? Well, it looks like we're only doing a two-dimensional problem, but essentially, though, since this is a cylinder, it's just going to project this circle in 3 dimensions. So we're just going to focus on this circle. And when we just multiply by the length of the thing, we come up with a volume. So we can figure out how to come up with areas of the circle that are roughly the same. Now, when I set this cross-section of the tank, clearly you're going to be half full when you just go right down the diameter. But if I cut this radius in half again and go here, I think you can see that that's not going to give you equal areas here for the 4 sections. So we're going to have to go a little less than halfway. So if this is a 2 meters from top to bottom, because the radius equals 1 meter, we're going to see that clearly at 1 meter we're going to be halfway full. So we're going to mark the rod at 1 meter for half full. But what about these now? This is where it's going to get a little trickier, because we have to look at how do we find the area of this segment up here. So we can go like this. We can say we need this area to equal 1/4 of the tank. So to do that, we want, this is basically a unit circle, and the area then for the whole circle is going to equal pi times the radius squared, so that's just going to equal pi since the radius equals 1. So we need this at 1/4 full, that this area of the segment has got to equal pi over 4. So we want to get that segment area to be pi over 4. Now we developed some equations for this, and that is the area of the segment equals the area of the sector minus the area of the triangle. And we're going to need some more information on here too, so let's call this conveniently alpha for the angle we're going to have in here. And the area of the segment is supposed to be pi over 4. The area of the sector is going to be 1/2 the radius squared, which is 1 squared, times alpha, which is in radians. The area of the triangle, this triangle in here like this, both these radii have 1, it's going to be 1/2 1 squared times the sine of alpha. So let's multiply through by 2, so we get pi over 2 equals alpha minus the sine of alpha. And so we got an equation here that mixes trig and a linear equation here, so there's no way you can do this just with trigonometry. So we're going to have the calculator solve this. So you can use your TI-89 to solve. I'm going to set this up on a GeoGebra thing to come up with the answers, but you can use this on the TI-89. You can use the solve menu, and let's see how that works out. Okay, so on my TI-89 I put in solve x minus sine of x equals pi divided by 2 comma x. And I made sure I'm in radian mode because we use that when we use this simpler formula for the area of the sector. So make sure you're in radian mode. And it gave me a little warning. It said more solutions may exist, and it gave me this solution of 2.30988. Now that's in radians, and that looks about right. That's less than pi. It's not 180 degree. It's less than, but still some obtuse angle, and that's what we expected. But let's make sure. Let's look at a picture of this. Make sure that there's another answer that we might be looking for. So I'm going to go to GeoGebra. Okay, here we are in GeoGebra, and I've graphed x minus the sine of x, which is something you can do on your TI-89. It's a strange looking graph. And now I'm going to intersect it with y equals pi over 2. And you can see we only have one point of intersection. And that point looks like it's at, let's intersect these two objects. The only answer we got, that 2.3 answer. Okay, so that's GeoGebra. All right, let's get back to the graph. Now, in the problem itself, here we are back at the problem now. Now recall that we found this angle alpha, and I'm going to cut this in half because it's an isosceles thing, so we can do our right triangle trig to figure out what that height is in the tank. So here we go. I'm taking this bigger triangle, which has this 2.3, this alpha in here. I'm going to cut it in half and just look at alpha over 2. So when we cut alpha in half, we get half of that. It's about 1.6, 1.15. And we know this is 1, and we want to find this little height y here. So let's use our triangle trigonometry, right triangle trigonometry. This is the hypotenuse. This is the adjacent side to the angle. So it's cosine. Cosine of alpha over 2 equals y over 1. So y equals the cosine of alpha over 2. And we can figure out then what we've got for that on our calculator. And we get 0.4039. So basically about 0.4. And so that's why we get these book answers here of going back to our diagram. this height here is 0.4. So we already agreed that at 1 meter, you've got it half full. If we go 0.4 up to 1.4, it should be 3/4 full. If we go 0.4 down to 0.6, it should be 1/4 full. So that's how you mark the rod that goes in. All right, that's it. Flange out.